We can plot the progress of a reaction using a reaction coordinate diagram, or an energy diagram it's also called. And what we have is a y-axis where the energy is plotted. This could be the Gibbs free energy or the enthalpy, or a lot of times I just keep it very generic and write E for some form of energy. The x-axis represents the reaction progress. And on this diagram, we always will have a starting material and a product. And to get from a starting material to a product, you always have to have at least one transition state. So what happens, the starting material will go over a hump. That's the transition state where bonds are being broken and made. And that is the highest point on this energy diagram. In this case, we have the difference in energy between the starting material and the product is more stable than the starting material. A reaction like this is a favored reaction, and we call this, if we're working in terms of enthalpy, delta H, we call this exothermic. If we're working in terms of Gibbs free energy, delta G, we call this exergonic. The energy it takes to get from the starting material to the transition state, that is your activation energy. Now let's look at a reaction diagram where the product is less stable than the starting material. In this case, we still have our energy difference between the starting material and the product, but the product is less stable. And in terms of how we describe this, if it's in terms of delta H, this is an endothermic reaction. If it's in terms of delta G, it's endergonic. And for the endothermic endergonic reactions, the sign is going to be positive. For exothermic exergonic, the sign will be negative. These two reactions are single-step reactions with no intermediates. If you have intermediates, those will also fall along your reaction coordinate. So the intermediates will be plotted if you have them, and generally your intermediates are always higher in energy than the starting material and the product. So say you have an exergonic reaction going from starting material to product. The intermediate is going to be somewhere above starting material and product. Let's say this is a 1 intermediate reaction. That's not a transition state though. The transition state happens when you go from one species to the next. So from starting material to intermediate, we have a transition state. From intermediate to product, we have a transition state. So we have 1 and 2. Whichever transition state is the tallest or the highest in energy, that represents your rate determining step. One way to just check your work for a reaction, the number of transition states is always going to be equal to the number of intermediates plus 1. So here we have 1 intermediate, 1 plus 1, 2 transition states. Here we have 0 intermediates, 0 plus 1, there's just 1 transition state. Here's a reaction that we looked at in this chapter where we converted this alcohol into this bromide through a series of mechanistic steps. And what we want to do is plot this on the reaction coordinate diagram. Now you are told a couple of things experimentally. One is it's an exergonic reaction. Second is that this second step is the rate determining step. And then third, we're told that this intermediate right here is more stable than either of the carbocation intermediates. So with that information, we can plot the reaction coordinate diagram. So let's start, and we'll just put the starting material on here somewhere. Then since it's exergonic, put the product somewhere lower than the starting material. I'll put it here. Now we need to put lines for our intermediates. And those should all be above starting material and product. So let's start with I1 and just put it somewhere above starting material and product. Next we need to plot I2. Well, we were told I1 is more stable than 2 and 3. So intermediate 2 should be higher than intermediate 1. Then we need to plot intermediate 3. Well, intermediate 3 is also going to be higher than intermediate 1, but what do you know about carbocations? I2 is secondary, I3 is tertiary. That means I3 is more stable than I2. So when I plot intermediate 3, it's going to fall somewhere between 1 and 2. So now we have all of our pieces put in. We need to just draw our line to represent the energies, and every step will go through a transition state. So we draw a line, starting material to intermediate 1. Well, intermediate 1 to 2 is our rate determining step. So that should be our tallest hump on the coordinate. Right, maybe I'm exaggerating a bit, but this is our rate determining step. Then we go from 2 to 3. It doesn't really matter how tall you draw the transition state as long as it's lower than the one for your rate determining step. And then finally, I3 will go to product. So this would be the reaction coordinate diagram for this particular reaction. We're going to continue to talk about these as we cover various reactions. So, if you're still not completely comfortable with drawing this, for this reaction right here, hopefully as we plot these for more and more reactions, you'll get a better feel for it.